Python programming is exciting. For me, Python's fantastic because of its simplicity. It's easy to enter into, the syntax is appealing and simple. This is huge because it lowers the barrier to entry into software engineering. And because of that simplicity, Python can essentially do everything. It's also the leading language for AI and innovations in artificial intelligence. Python can also be used to enable network level communication. You can build Python applications that can communicate across various machines and data types. Any kind of data that you want to send between one machine and another, you can do with socket programming. Python gives you access to this capability, and it's very powerful. You might say, oh, Python's a slow language, it's not very capable. But when you look underneath, a lot of the power comes from libraries that are imported and are directly accessed from the Python interpreter down into C languages that are compiled and built for your system. So even though you're programming in Python, you're using the power of C and other compiled languages. Socket programming in Python is actually fairly straightforward. We're going to try it out. Socket programming is critical to understanding how the internet works in general. It allows you to communicate with any other machine wherever it matter be. This kind of programming is used to coordinate systems across various modern web stack applications, including database connections, web servers like Nginx, and being able to communicate with devices like your phone. All of that's done through socket programming, and guess what? Python can do it pretty darn well. We're gonna try it out here. Is Python good for socket programming? Yes, it is. There are a lot of options when it comes to selecting what libraries you'll use for socket programming. For high-scale systems, you're gonna wanna use an event-based engine that allows you to receive interrupts directly into the Python language. You can capture those interrupts and then act on those activities to create a request response server, or just to stream data in to collect telemetry. You also get to choose what underlying level 4 you're going to be using on the network, which is talking about the protocol, the underlying protocol of the packet. What kind of packet is it going to be, right? What's that fifth tuple? Are you going to be using TCP or UDP? The kernel, once it understands what kind of communication pattern you're going to be using, will be able to leverage advanced capabilities of TCP that have retry of packet delivery under failure conditions, or UDP, where it just is Wild West. Whatever you ask the socket to do, it is going to do it, but it might decide not to retry any of the data delivery, right? It just won't, because it's UDP it's like a connectionless and lightweight protocol for applications, and packet loss is possible, whereas TCP has a built-in retry mechanism. But even with that, you can still lose packets like crazy, because if the device goes offline, there's no way to get back in touch with the device. You're going to be losing data, and that data is unrecoverable. Socket programming in Python is really powerful because it's so simple. They make it really easy. We just import a library, and then we run a few commands, and now we've got connectivity. Before we dive in with code, let's walk through exactly kind of how things are connecting together here. So we've got our Python application, which is where our code lives. Then we'll be accessing various libraries that enable communication, and it kind of sits on top of a lot. The internet, there's a lot to it. We've got your protocol, TCP, UDP, we've got the internet with IPA. There's so many layers. Let's just take a quick peek at the layers of the internet. Day to day, as software developers, we tend to see that the application stack, when communicating over the network, we tend to live at these top layers here. For the most part, we don't know what's going on underneath. There's a lot to it. The top layer is where we spend our day-to-day, and that's layer 7 at the application layer, where we interact with APIs, typically a REST API, and the data payload that goes along with it, which is typically JSON. And often, that's as far as we need to go. We don't need to go any further than that when we're dealing on a day-to-day basis with internet. The next layer down, we're still typically familiar, layer 6, the presentation layers, things like HTTP and WebSockets, but also where the encryption occurs. Represented in this diagram, we see things or hear things about security and encryption, TLS, transport layer security. We typically kind of bucket into these two layers, 6 and 5. A session is maintained that keeps track of connectivity based on ports. We can also have a session ID that's used for cipher key caching that allows you to communicate with devices with encryption without having to regenerate a cipher key, which is computationally expensive. Usually layer 5 is where everything is taken care of for us. We don't really need to look beyond that. We don't have to make many decisions because the kernel will take care of everything else for us, as well as all the layers in between. The transport layer, typically known as TCP or UDP, defines how the computers will communicate between each other. TCP has a built-in mechanism that allows it to retry missed packets, anything lost in transit, through sequencing IDs and timestamps and other kinds of things, as well as congestion mitigation. TCP has a lot of things baked in that make communication more seamless, whereas UDP is a protocol that is whatever you want. You send data packets. The data packet might get there. It probably will get to the other side, but it might not. And there's no built-in expectation of communication, whether that data got there or not. What you'd want to do in that case is build in, if you want more reliable UDP, build in like sort of an acknowledgement layer. But now you're starting to creep into the TCP world. Layer 3 is also known as sort of the IP address, which helps decide where packets need to transit across the internet. This packet has this IP and the source IP and the destination IP, and it needs to get over that direction. And so it will hop along the way based on the information that's in the Ethernet frame, which is typically, it looks like what we have is the link layer, which is layer 2, kind of like the whole format and guide of every single one of those packets. Right now we're one step above the hardware layer. The physical layer, which is the bottom, which are going to be your routers, your switches. Those devices are just going to follow the rules in general of trying to make sure to transmit data to where it needs to go. There's a lot that's missing from that overall. It just seems like it's a lot. There's a lot with the internet that goes on with every single packet that goes through that's a lot of data, and that's a lot of layers. Let's do it. Let's build a Python application that's able to communicate using sockets. Let's get started by creating our first file. What we're going to do here is we're going to follow these instructions to create a client.py file. We're going to copy this really quick. We're going to paste client.py over here. And then it also instructs us to copy this. It's probably going to be server.python. Yeah, server.py. Here we go. Server.py. There we go. All right, now we've got two files, a client and a server. Let's test it out. Let's see what happens. All right, we'll follow these instructions to run server.py first, so that way we can bind to a port that will be listening for interrupts from the operating system to receive data. When we receive that data, we can then execute instructions that we define in the Python code to do anything we want. In this case, it looks like what we're going to do is appears to be a simple echo. Well, no, not really an echo. It's just going to say, hey, I'm a server. All right, it's going to print the data that it received from the client, which in this case is I'm a client. And then it's going to respond to the client and say, I'm a server. So we're not echoing the data that was sent to us. We're just going to send an acknowledgement. All right, let me set up here really quick. I'm going to open up two terminal windows, one client and one server. We'll run the server first, Python server. Now our server's running. It's waiting for data to be received. Let's see what happens when we run a client. Well, the client code is just simply going to send a request to the server, Python client, and here we go. It did it. It did the thing. So the Python client sent information that I'm a client over to the socket. At this point in our diagram, we are only basically discussing the layer 4 because we're dealing with IP addresses, and we've chosen TCP, and the rest we're kind of programming since we're using sockets directly instead of maybe a requests library or a fetch library that takes care of the rest of these things above. We're using just the raw socket. So there's no encryption. It's just data through Ethernet frames, and we're just dealing with layer 4 at this point, which gives us a lot of control. So our client code sent I'm a client to the server. The server received it. The server responded with, hey, I'm a server, and then the server ended the connection. Now, the server could choose to leave the connection open and continue to communicate with the client. And this is usually how game servers work. A game client will connect into a server along with a whole bunch of other clients so they can communicate with a central server that holds the world state of a view of a game. With this simple example, I should be able to, I can keep running the client saying hello, 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 and the server responds with a, hey, I'm a server, I got your data. Python is great for socket programming, and we just took a look at the source code written in Python that allows you to do these communications. Very simple. It's super easy. Check it out. Let's walk through the code that it takes to create a server that can connect clients in and allow them to communicate to each other. So starting off here in our code editor, we import the socket library for both our server and client. Now for front-end developers, we typically don't dive much into the server side of things. We will typically have general communication patterns like this. Here at the top of the screen, we have our client connector. The client connector has an IP address that's usually resolved through DNS or a domain name. A domain name like pubnub.com will resolve an IP address that will be connectable. An example like this, you can connect to the IP address. Then the client sends a request. In this case, it's a simple string. However, you could also send formats like HTTP with a header detail and a payload in the body section. On line 4 here, we send our data, and then from there, the kernel, the operating system, and the rest of the internet will take care of everything for you. Now, there's problems that can go along the way that we should probably check for, right? Just in case the data fails to get delivered or we wait too long to hear a response. Just keeping things simple for now. This is basically all you need to do. Send data, and then you can wait for a response here on line 5. While the client is waiting for a response from the server, essentially your data is transiting the internet at that point, and then it will eventually get received by the server code. So we see here that line 6 corresponds to line 3 in the server code. So we've got a server, we're waiting for a client to establish a connection. We create ourselves an empty variable that will pull in the data that the client is going to send to us. We wait to receive the data. Now that we've already established the connection, we know we're about to receive data because that's our expectation from a server perspective. In case the data is broken up into chunks, we want to concatenate that data into our variable for the buffer. Line 12, we print the data so that way we have that information in our, this is like typically an access log, right? So maybe it's an HTTP request. This is where we would log that data in an access log. Then based on what the client was asking, we send them a response. In this case, we're just gonna say, hello, I'm the server. I got your data and I logged it. So this is actually a really good example for something that you're gonna collect telemetry for, where you just simply want to collect information, but you're not really gonna perform any actions. This is a really great boilerplate for that kind of scenario. When you're developing with Python and sockets, there are a couple of interesting constant values when you're initializing a socket connection. There are these cryptic acronym-based constants that you would see in example code when establishing a connection between a client and a server. From the Python socket library, we see the AF_INET. This constant is going to tell you the address family that's going to be used for establishing connections. Basically what this format is going to be here when I'm looking at what I'm going to connect to. What does that address family look like? The common standard, maybe even the default, is IPv4, which is what we're looking at here with the 4 hexadecimal values, typically represented in decimal, which is 0 to 255. The version above that is INET 6, which is the IPv6 version, and it has a lot more, it's got a lot more digits in there. IPv6 has 4 times more bits. 32-bit in IPv4 space compared to 128 bits in IPv6, which means in IPv4 you can have 4 billion addresses, comparing that to IPv6, which is, what number is that? No. That's a huge number. Basically, we're like, IPv6 has a limit on the number of devices. We thought 4 billion was going to be enough. It's not. With IPv6, we're like, okay, let's just go all the way. There is so many everyone in the world can have an IP address. With IPv6, all of their devices, everything just is going to be insane. It can have its own IP address. The second parameter in our socket initialization for a client and the server is going to be the kind of communication packets that are going to be transiting over that communication connection. Things like TCP and UDP. The default is going to be TCP. You do not need to specify, I do believe you don't need to specify this particular entry here. This isn't necessary because that's just saying we're going to stream, it's a TCP connection. It's intended to be a long-lived session where you communicate between the client and server, and it requires a handshake procedure which allows the operating system to maintain a table entry for a connection ID, usually represented as a file descriptor, and in the kernel's network table will hold information about the source IP, the destination IP, and the source port and the destination port. The destination port's always going to be the address of the server, and my local port is going to be generated by the operating system. It's usually going to be a large number above 1024. We could change this parameter here to instead of saying like a TCP stream to be like datagrams, which are going to be UDP protocol. So we're still using Ethernet frames at that point, which allows us to specify Ethernet protocol, and it will be a connectionless type communication. So I don't need to have a handshake between the client and server. I can just send packets, boom, shoot packets off, and the other side will receive those packets. So I think it's something like sock_datagram And you'll want that to match your server as well if you're going to be communicating over UDP. Yes, all right, so SOC datagram. The other one is SOC raw, and this is where it gets exciting. This gives you full control over layer 4 and 3 with the raw, because you get to construct the entire Ethernet frame from scratch. And that gives you a lot of control, because you could, this is where security comes in. If we dive in even further, you'll have a lot of control over the network. You'll be at the whim. You'll have the internet at your fingertips. We won't cover that, though it is a good one, and maybe someday we'll cover that topic, because you can do a lot there. Socket programming in Python is really powerful and fairly straightforward. However, there's a challenge once you want to extend outside of your local area network to enable communications with devices that are a distance away. There's more to the picture. So we showed an example of leveraging Python to create an application that allows you to communicate between a client and a server. This is a low level of communication, typically the lowest that you'll ever go in types of communication when talking over the internet between devices. The problem comes in when you need to communicate across distances, right? Where the device is outside of your local area network. You'll typically need to take that server.py code base and then put that onto a server, open up a port, fix a DNS entry with an A record pointing to the server, so that way you have an IP address that can be looked up in a client connection device. The client will resolve the DNS address and then connect over to the server on the IP and the port. That's an extra step that you need, but it goes even further. Servers have a reliability issue, especially cloud-based servers that are on shared tenants. After a while, these servers will wear out, or there's ways that they can fail either through a disk network failure or another kind of network failure. So what you'll need is redundancy built in, and having multiple servers is typically the way to go. And even today, what you need to do is go beyond just a single data center and having additional reliability by having multiple data centers. All companies typically large enough to support the need for this level of reliability have multiple data centers. And so you need to build in additional reliability configurations. As clients connect, they need to know which region is active and alive. They also need to know how to connect into the proper segment that's going to be interesting in terms of communication, right? You might have a thread or a conversation that one particular set of servers will be managing, whereas the other set of servers won't, and so you'll need the client to be able to understand how to connect into that. And so that's a lot of infrastructure, that's a lot of architecture. What happens during failures? How does the client know where to hit the next region? What kind of routing do you have? What kind of load balancing? There's a lot to deal with. So if you want to make it super simple, this is where PubNub comes in. With PubNub, you can use the SDKs that we offer with Python and JavaScript and any other language, Swift for iOS, Kotlin for Android, and all these different languages and libraries can communicate with each other seamlessly. And you don't need to deal with DNS, IP addresses, TCP connections, security, data sovereignty. There's a lot that goes into it. So we take care of all of that for you seamlessly. You just install the SDK, then you establish a listener by defining a function, a message received event. And the great part is the client can also act as the server, and this is sort of a decoupled mechanism that allows you to easily communicate to any device anywhere, whether it be local on the same network or remote. All those complexities of dealing about what kind of connection it is abstracted in a way that makes it super seamless. So now you can have an Android and an iOS device, a web browser, a server. They can all communicate together using the SDKs that are native to their platform. What happens if the device disconnects, but I'm trying to send you a message from another device? Well, PubNub has a built-in store and forward mechanism that allows the device that missed the message to ensure that it does receive it the next time it comes back online. All these things, these little problems that you would run into for network communication, these are the kinds of things that are solved using the PubNub platform. Taking advantage of the PubNub's edge messaging network, your device will connect to the closest data center. We run on AWS using Kubernetes that are deployed in all of Amazon's AZs. Availability zones. As a message is sent in through the network to be delivered to a target device, PubNub will automatically replicate that message across the regions that are specified. This is that store and forward mechanism that we were describing earlier. As clients connect in, they can choose to receive the latest details that they may have missed, or just proceed onward from where they are currently. This brings with it a high guarantee of reliability when communicating with devices over the network. And it goes even further than that. You might want to know if the device is actively online. Is the device active on the network right now? Is it available to receive messages? You can know this using PubNub Presence with their online-offline events. So we have the current state of the device if it's connected to the network or if it's offline. And there's even more to the picture, but we won't go through all the details this time around. Of course, one of the major aspects for communicating over the network is security. You need to make sure that only the authorized users have access to the data, so when data is being exchanged over the internet, secure through encryption, data locality, and those users who have permissions to read or write data onto the network.